And then we'll gradually start talking about how to do stability analysis in physics. So to start with, we started with the Newtonian laws, Newton's second law to be precise, that dp dt is equal to net force, right, where P is the momentum and P is mv. The equivalent equation in for rotating objects, rotating solid bodies, is dl dt is equal to tau, right? Where tau is the torque, and tau is defined as I inner product with omega, and I is the inertia tensor, and we talked about that. Now these two equations, we always, when we discuss Newton's second law, we normally discuss it in terms of inertial reference frame, right? So that there is no fictitious force or nothing appearing in that equation. But in this case, when we are talking about rotating solid bodies, it's preferable to do it in the rotating body frame of reference. Why? Because when an object is rotating, as you saw that it can tumble back and forth or moving like that, if you just look at it from the inertial reference point of view, then all these x, y, z axes are changing, right? But if you fix the coordinate system with the body, then even if it is moving back and forth, say about the z-axis is not changing, right? So it's better to do it in terms of the body axis or body reference frame, rotating reference frame. And we proved in the last class that any vector, whether it's L or A or B, does not matter. The relationship between inertial reference frame is equal to the same vector, the time difference with respect to the rotational reference frame or body reference frame, plus omega cross that vector here in this vector is L. Agreed? So now we will see everything from the rotational axis frame or body, the frame which is attached to body. Now for torque-free motion, we know that tau equal to 0. That is, you have given a spin and then let it go. So there is no other force, which is equivalent to F net equal to 0. So in that case, what will happen? That's our point of consideration. So my dl dt from the inertial reference frame is equal to 0 because dl dt is equal to tau. So right hand side is 0. So I can write it. From this equation, I can write it dl dt plus omega cross L equal to 0, right? And from now onwards, everything is in the rotating frame. And this equation gives rise to the set of Euler's equation. How can we get the Euler's equation from here? Just by using the formula that the relationship between angular momentum and moment of inertia and the L equals to dl dt, L is equal to I omega. So here I have made a mistake. So this is not tau, this is L is equal to I omega, right? So the angular momentum vector is equal to I omega inner product. So L is equal to I omega. So that means dl dt is equal to angular momentum vector inner product with omega dot. The first term I can write it is as I xx omega x dot plus j I y y omega y dot plus k I z z omega z dot. Agreed? Right? So this is plain and simple, right? So what about the other term? Other term, so this is from this term I got that. So omega cross L, we get it as, if we break it down into traditional form, cross product omega x, omega y, omega z, and then I xx omega x, I y y omega y, and the third term I z z omega z, and then I can write it as is equal to I, and these two multiplied by these two. So omega y and omega z will be multiplied with the both terms, omega y y omega z, and then this is I z z minus I y y plus j, and this so omega x omega z, and then I have I z z minus I x x plus k, and k I have this omega x omega y, and then I have I y y minus I x x. So this is this plus this equal to 0 if I separate all the terms. So just one more line let me write down because I want to make sure that all the calculations are correct. So I x x omega x dot plus this is I z z minus I y y omega y omega z equal to 0. Separating the items, this one is equal plus this term equal to 0. Similarly, I y y omega omega y dot plus I z z minus I x x omega x omega z equal to 0. I z z omega z dot plus I y y minus I x x omega x omega y equal to 0. Can you check if the equations are correct? Let us see. I x x omega x dot plus I z z minus I y y omega y omega z equal to 0. I y y omega y dot I, here there is a negative sign there. I should be this minus this omega x omega z plus I z z omega z dot plus I y dot minus I. So here I have.
It's just a question, Dr. The first time I see the I x y is not in all this.
Oh, this is no
this one. First one here. Yes,
Percent-
yes.
Oh, this is XX.
Exact, yes.
Yeah. So let me see. This one is Ix minus IZZ. Oh, so here I made a mistake. Ix minus IZZ. Ixx minus IZZ. So it should be the other way around. So because when you are taking the middle term, it's the opposite. Yeah. So this is the three Euler's equations. So this is how we get Euler's equations. So this is pretty plain and simple. Now we will talk about how we can do the stability, analyze the stability of these equations. Now, first of all, let me go into the physics of stability, and then I will discuss what it means by stability analysis.
Okay, and this here is JIXX, not X1.
Excellent. Yeah. Okay, so first of all, let us think about stability from completely physical point of view. Suppose you have a bowl like this, and you have put a, say, iron ball. Sorry.
Somebody's asking what courses.
Oh, okay, yeah, coming back. Okay, so if you say have a bowl like this and you have a steel ball here, what do you think, whether this configuration is stable or unstable? You have a bowl and you have a steel ball there, sitting there.
Stable.
Stable. What about this one? You have a heel and then there is a ball sitting there.
No,
Unstable.
Unstable.
understand.
Suppose you have a billiard ball, a table, and you have a ball sitting here.
Stable.
Stable. This point is stable. What about if the ball is sitting here?
Stable.
Still stable. If it is here,
Not still stable.
still stable.
Yeah.
So this is like intuitively, we know which points are stable, which configurations are stable, which configurations are not. Now we will find out how can we test that mathematically. Okay. So what we can do is, the ball is sitting there, so these are sort of the base state. That means the state from where you are starting. It's your starting point. Okay. So these are, say, base state. We call it base state. And now what we can do, we can give these balls a small perturbation, right? So first of all, we define the base state. Number two, we perturb the system, and then what will we do? We perturb it. Perturb means that we'll say we pull the ball here and let it go, and then we'll watch what is happening to the ball. In this case, what will happen?
Oscillation.
Oscillation, and eventually, if there is friction.
It'll be a damped oscillator. It'll settle to zero.
Very good. So here we can say this is the perturbation. It goes back and forth, and then eventually it will come back to the original position, right?
Yeah.
So the perturbation dies down. So if the perturbation dies down about the base state, we call it stable state. In this case, suppose you give a small perturbation in either direction. So in terms of the perturbation, what happens to the perturbation? what is the time evolution of the perturbation?
It'll grow.
It will grow in time, right?
Yeah.
It will grow exponentially.
Yeah.
It will never come back. What about in this case? We give it a kick or perturb it, it comes to the new position, it's still the stable state, right? So these are the first two steps. We define the base state, we perturb the system, then we watch the time evolution of the perturbation, right? That there can be at least two options. Is if the perturbation grows in time, we define it as stable, and number two, if it dies in time or decays in time, let me use the term decay, if it decays in time, we call it, I'm sorry,
Unstable.
the other way around. If the perturbation grows in time, we call it unstable. Unstable. If the perturbation decays in time, we call it stable. There can be additional situations when the perturbation can oscillate in time. This is the more advanced, which we call the oscillatory stability or Hopf bifurcation kind of thing. But we will not go in there. We don't need that at this point. So this is stable. This is unstable, and this special situation is called neutrally stable. Again, we can have, say, a special configuration like this. If the ball is here, then if the perturbation is such that the ball can escape this hill, it can end up to a completely different stable point. So this is, but if the perturbation is small, it will come back here. But if the perturbation is such more than this, say, energy barrier, then it will end up to another stable point. So this is called locally stable point, and this is globally stable point. Globally stable point, right? So if it is here, it's globally stable. If it is here, it's locally stable. So we call this kind of situation as metastable state. Metastable state, when the particle is here. In laser and other areas, we use that metastability a lot. So this is the physics of stability that we can see the connection between the actual situation and the mathematical form. Now, in physics, whenever we see these equations, this set of equations, they're describing something very physical, tangible, in this case at least. So, what is this? These three equations telling that there is a solid body rotating, and these are the connections between the moments of inertia and their the angular speed, right? How the angular speed, angular velocity will evolve, and these are the components of angular velocity. How they evolve in time, or how they are connected, how they are entangled, how they are should not say entangled because it's so much used in quantum mechanics, how they're coupled to other moments of inertia, right? So these are three coupled ordinary differential equations where the time evolution of each of the angular velocities or time evolution of each of the components of the angular velocities is coupled to the other moments of inertias and other angular velocities, right? So when we see these three equations, the picture a physicist sees is that a solid body is rotating, right? These mathematical equations are nothing but to describe the rotation, right? Okay, now
I have some confusion.
sure.
In my mind, maybe because I'm not physics, but everything talking about the velocity, some related to time.
Mm-hmm.
But I didn't see any time included in this equation.
Oh, this is the dot. This is omega dot. That's the time derivative.
Oh,
Right?
All of the
So
functions are
I've
dependent on
shortened
time.
it. D omega dt.
angular, yeah.
Yeah. I have a quick question too.
Sure.
So go back to the bowl right? Analogy. So the one at the top, right?
Yeah.
It has a to the right, the locally stable.
Mm-hmm.
That one is at a higher potential than the one in the bottom. Probably on the one to the right.
This one? No, suppose they're all in the same energy.
I'm saying the one to the right.
This one?
No, one more. One more.
Oh.
Yeah.
Oh, I'm sorry. Yeah,
So that's in metastable state,
metastable
right?
state,
Because
yeah.
if the perturbation is large enough, it goes into another stable state.
Yeah.
Now, the one in the bottom basin,
Mhm.
that is also metastable, right? It just requires a larger perturbation to go to the other stable state.
It could be, or it may not be. It could be say if we talk about this floor and this table and this arrangement. So this floor it has the lowest gravitational potential energy in this room, right? But it's not the lowest if we consider the whole building. The ground floor has the lowest potential energy, gravitational potential energy, right? But if we say that the floor is weak and you are somehow holding a heavy box, say it's made of just straws and things, and you are holding a heavy box there, and say one small push will be able to break those straws, the binding energy of or bonding of the straws. Then when the heavy box was kept here, it was in a metastable state. It's going down to attain the global stability. It is in local stability now.
Yeah.
But it can go back down to global stability. It depends on the energy landscape. So this is called energy landscape. In terms of energy landscape, and these terms will arise in many different areas. Say sort of why two molecules will bond and when it will bond. When it has to minimize the energy.
Lowest energy state.
How the proteins will fold. It has to minimize the energy. Now there is an interesting question that protein folding, that it can have like the millions of different configurations before it falls into a certain configuration. But proteins jump to the minimum energy configuration without going through all these small energy minima. How does it know that, or what is the mechanism? These are still open questions. And now AI is getting used very heavily in those computational efforts. Google DeepMind. Actually, Google got a Nobel Prize this year or the last year because of this protein folding and using of large language model and the whole application of AI in this field. And now there are several other companies are doing that. Okay, so this is Now let me give another example. Suppose we talk about, say, this notebook. When we place an object here, this object is stable. Now this is still stable. The friction force is holding it, right?
Yeah.
But if I give a little perturbation, then it goes down. So although the object is still in place, this is not a stable state. So this using perturbation is fundamental, right? Whatever the situation may be, I will use some perturbation and see how the perturbation is doing, or what the perturbation is doing, right? So this is the fundamental idea. So this is here, and I'm using a small perturbation. That means here a little displacement, that's the perturbation, and the displacement grows in time. So the object never comes back to the original position. So we say that this is an unstable situation, right? So mathematically, how will we do that? We can take a base state. What is the base state? So let me define our base state in this situation. So define our base state. Our base state. Say our base state is, say, the object is rotating about x-axis. So the three omegas, omega vector is, the three components are, say, omega, capital Omega, and 0, 0. Agreed?
Mm-hmm.
That's my base state. Now we will perturb it. How can we perturb it? So perturb this base state. What we'll do, we'll take another omega, which is the perturbed omega, is we keep the omega as the same. I will add little bit of wobble in the around the y-axis, and little bit of wobble around the z-axis, epsilon z. What are these epsilons? Epsilons are very small number in comparison to the original rotation speed or angular velocity. What does it mean? It means that, say, if omega is say 5 rad per second, or epsilons are or could be of the order of 0.001 rad per second, like that. For example, this is just an example. It can be smaller, it can be larger, but they are order of magnitude smaller from this one, right? Order, at least one order of magnitude less than that one. So then what will we do? We will use these omegas in these equations, and then we'll see what is, and so this is not time dependent, this is constant, but these perturbations are time dependent, and we will see what is the solutions of that epsilons, whether epsilons are growing in time or shrinking in time. This is exactly the same thing, right? So if we don't go over this, it will look like a complete jargon. But this is basically exactly what we did here. We added a perturbation and we watched what the perturbation is doing. Here also we added small perturbation. But how we are ensuring this smallness? By making epsilon very, very small, order of magnitude smaller than the base rotational velocity. And then we'll see how the epsilons are behaving in time. Ready? So, ready to go to the next phase?
Yeah. So, capital omega.
Yeah,
It's constant.
constant.
Okay.
Because you have given a speed.
Yeah.
So in your experimental case, when you are rotating it,
Mm-hmm.
that's when it's a free rotation.
Mhm.
That's the speed. That's omega.
Yes.
And then, as you said, it's not completely stable in the z-axis. There could be, when it is rotating, there could be some additional omegas.
Especially on release.
And it will be always. There will be some error coming from somewhere.
Yeah.
Either from wind resistance or from the payload, or if you rotate it by hand, you cannot be perfectly symmetrical without any other sort of perturbation.
I'm getting a little bit ahead of us right now, but I'm thinking. So that omega x dot term, that term's going to go to 0.
That omega x dot term going to
Let's go to 0. So we're assuming, I'm thinking in our case, right? If this is our object spinning around z or x in this case, right? We're assuming that it doesn't cross.
We are not assuming anything at this moment.
Okay.
Yeah.
Okay. Because I'm thinking. Okay. Yeah.
Yeah. So, because in your object,
Yeah.
this state and this state are the same energy states.
And the rotation actually is the same velocity. It's just the reference frame of where it is.
Reference frame?
Yeah. Okay.
So,
I'm with you.
so these are the same energy state
Yeah.
and same angular momentum state.
Yes.
So remember, last class we talked about this point source construction, where we showed that the angular momentum sphere L square has to be constant, and the energy ellipsoid is constant of time.
Yeah.
So both of them have to be satisfied.
Satisfied. So you have to have a sphere that's also intersecting with the ellipsoid,
Ellipsoid.
and that's how you're going to develop your
that's
path.
the
Okay.
separatrix, right? So this is, now we are almost there in a position to analyze, and you are absolutely correct that we don't have to worry about this equation. We'll focus on these two equations, and then on top of that, these two equations are coupled, right? So if we use these special type of angular velocity in these two equations and solve these two coupled differential equations to see whether omega epsilon y or epsilon z, their behavior, if they're decaying in time, then we'd say that's stable state. If they're not decaying, rather they're growing in time, we'll call it that an unstable state. So define our best state like this, and imagine and consider this case. Ixx is less than Iyy and less than Izz, or opposite, Ixx is greater than Iyy greater than Izz, both cases where one moment of inertia is in the middle between the two. So now ready for the for doing the perturbation analysis. It's a little bit of math, but not too scary. Let me go for that step by step. And once you do it, you will see the beauty of the whole process. Okay, so I will just plug this in these two equations. So let me just name it equation number 2 and equation number 3. Let's call it equation number 1. So these are three Euler's equation. So from equation 2, so let us do it from equation 2. What we get from equation 2? That I, y, y, and instead of omega y dot, what I am putting here now is epsilon y dot, right? Epsilon y, and that's differentiated with respect to time, right? What is the second term? I xx minus I z z, and then we have omega x and omega z. What is omega x? That capital constant omega. Omega z is epsilon z. So capital omega epsilon z, and that is equal to 0. So let us do one more step. Let us from here I divide both sides by I y y. So epsilon y dot plus I x x minus I z z divided by I y y omega epsilon z equal to 0. Agreed? If there is any mistake or any typo, don't hesitate to stop me and ask me. But from this equation, I see I z z. This would be epsilon z dot, right? So what we can do, I can differentiate this equation one more time with respect to omega, so that I can get epsilon z dot, and then I can directly replace this epsilon z dot from the third equation to make one variable thing. So now differentiate it one more time, and what we get, epsilon y dot dot plus I x x minus I z z divided by I y y omega epsilon z dot equal to 0. Apart from these two things, everything is constant in time. Now we have got a clue, epsilon z dot. So let us see from here, from the third equation, what do we get epsilon z dot? If I plug the same form here, I get the perturbation equation 3. I get I z z omega z dot, that means epsilon z dot plus I y y minus I x x. Omega x is that constant capital omega, and omega y is epsilon y, that is equal to 0. Any doubt? Agreed? Okay, so that means epsilon z dot, I will bring this whole thing to the right hand side, and I will divide it by I z z. So when I bring it to the right hand side, I can switch the terms because I'm multiplying it by -1. So I get I x x minus I y y divided by I z z, and it's multiplied by omega epsilon y. Agreed? So I got this equation, so let me call it 4 and let's call it 5. So let's plug this 5 into 4. Plug equation 5 into equation 4. I'll just replace this epsilon z dot from that equation. So we get, what we get from this equation 4 is epsilon y double dot plus I xx minus I z z, and then I have got I xx minus I y y divided by their I y y from here, and then there is I z z from equation 5, and then there is multiplied by omega there, capital omega, here capital omega, so omega square, and epsilon z dot, there we get epsilon y equal to 0. So now
But the 2 times is second derivative?
it's a second derivative, yeah. So now everything is only one variable.
It's a linear differential equation.
It's a linear differential equation. What type of linear differential equation? X square minus k square x equal to 0, that equation, right? Sorry, x double dot, not x square, x double dot.
Yeah.
X double dot minus d2x dt2 minus k square x equal to 0, and depending on the sign of this whole term, we know whether x will be growing in time or decaying in time, right? Because the normal procedure in solving this type of differential equation is assume x is equal to e to the power sigma t and replace it, and then check sigma is positive or negative. That's the thing. So now look at this term. So what is our assumption here? We are rotating this object about the x-axis, and the middle inertia is larger than xx and smaller than zz. So this term xx minus ixx minus izz. So what is this term? Positive or negative? Ixx is smaller. Say, consider the first one. This one.
It's negative.
Negative. What about this one? Ixx minus iyy.
Also negative.
Also negative. So this negative is positive.
Positive numerator. Yeah.
Hmm? So when we bring it to the right hand side, it becomes negative. So e to the power x negative t thing, right? So this is a stable state. So when it's still intermediate, but you are rotating it about the x-axis, then it is stable.
Because the time evolution, if that sigma is negative, it's going to decay to 0.
Yes, it will decay to 0. So x, if we look at it, that's the starting point, it will go to 0 as time. But if you do the same analysis with when the second perturbation analysis, if you take omega perturbation is equal to epsilon x omega epsilon z, the same thing, but now you have this intermediate moment of inertia, but you are rotating it about the intermediate axis. If you do the same analysis, you will see that the right hand term will be positive. And I would suggest you do this analysis by yourself. When you do it on paper, you will you will find it. If you have any difficulty, I will help you out.
Yeah, it
But-
parallels control systems very
Exactly.
well, very similar.
Yeah, same thing. You have done it. I mean, in physics class, you have done it in
I did it yesterday actually.
Yeah.
yeah.
So now you do the same analysis and you watch what will be the perturbation. In that case, you will see the perturbation will diverge. So that would become unstable.
Mhm.
So this is the analysis that proves when it will become stable, and it's connected to mathematics, right? Mathematics is not disconnected from the reality. So what the examples that we are giving, that when suppose this is the intermediate axis and you are rotating about the intermediate axis, you have this situation and this situation. Both the situations, the energy and angular momentum are conserved. So if you have some instability, that instability is growing, and where it is going, it reaches the second stable point.
Mm-hmm.
So it started rotating, wobbling around the second stability point.
Mm-hmm.
But then again, there is some perturbation, so it overshoots it. It's come back to the other stable point.
Mm-hmm.
Again, it's not perfectly rotating like this. There is some wobble, so it becomes unstable. It's going back. So that's what is happening, going back and forth.
And if it's truly zero torque and say it
will
go
be unstable.
forever.
Forever.
Yeah.
Exactly. So that's the whole analysis of the Dzhanibekov effect, and this has become so. This is actually some counterintuitive for some people, not for some people, almost everyone. Even Terry Tao, jumped into in one of the online discussion forum, and a couple of years back. It's not like, and Terry Tao is considered one of the smartest mathematicians in our generation, like Einstein of our generation kind of thing. And he was so interested in this analysis, and this is basically an undergrad analysis. There is nothing very special, something like that you cannot understand or you cannot derive, right? But you need proper perspective. That's the whole point. That what is stability? How do we analyze stability from physics perspective, from physical point of view, and from mathematical point of view. The beauty of physics is that they are always connected. In mathematics, you don't care whether this system of equations really describe
Translates to a physical system.
some physical system or not. Mathematics is beautiful in its own, has its own charm, but there is no obligation that it has to be connected to some physical system. You can play with mathematical equations and find beautiful theorem and conjectures and everything, but in physics it has to be connected with some guiding principles of the universe, right? So this is what the guiding principles are. These are coming from the conservation principles and energy principles, and we have connected it to the stability theory, and we showed why the intermediate axis rotation about the intermediate axis will become unstable. Make sense? Very good. Okay, thank you.